The first derivative shows the slope, and the different configurations of slopes can clear out the concavity. Learn how to use the first derivative test here in differential calculus. What are parametric equations? These are equations or functions which are written as a function of another variable. For instance, we have x as a function of t, and y also a function of t. The variable t is called parameter, and in parametric equations, the usual parameters used are t and theta. Let's have an example. Say x is equal to t, then y is equal to t squared. Let's use a table to find values of each variable. Take note that t is the independent variable, and both x and y are the dependent variables. Assuming t of -3, x turns out as -3, and y is 9. When t is -2, x is also -2, and y is 4. At t of -1, x is -1, and y is +1. At t of 0, x is 0, and so is y. Then when t is 1, x and y are also 1. At t of 2, x is 2, and y is 4. And if t is +3, x is 3, and y is 9. Connecting the dots in the Cartesian plane, we can identify the curve. How about taking the derivative of parametric equations? How do we come up with the first derivative, which is dy over dx, when the functions are in terms of t? There are two methods we can come up with the derivative. First is through derivatives. Having two functions, x and y, take the individual derivative of each function. Take note that since they are both functions of t, the derivatives turn out as dy upon dt and dx over dt. If we take the ratio of dy over dt with dx over dt, we can then eliminate dt, which then results to dy over dx. The other method is through differentials. Having the two functions for y and x, take their separate differentials. Dy is then equal to the prime of the equation with dt. Then dx is the prime of the function times dt. Next is to take the ratio of dy over dt, where the dt's at the end also cancel out, leaving dy over dx. The third example contains the parametric equations x of 1 plus t squared and y, which is t cubed minus 2. The first derivative is dy over dx, but we can only reach to this configuration after taking the derivatives of the parametric equations with respect to t. So with x of 1 plus t squared, differentiate with respect to t. The terms can be separated, so dx over dt is then the derivative of 1, which is 0. Then take the derivative of t squared, which is 2t, and attach the derivative of t with respect to t from chain rule. dt over dt is 1, simplifying dx over dt as 2t. For the other parametric equation, y of t cubed minus 2, the terms can also be separatedly differentiated. So dy over dt is then the derivative of t cubed, which is 3t squared. Then attach the derivative of t with respect to t from chain rule. Subtract the derivative of 2, which is 0. Again, dt over dt is 1, making dy over dt as 3t squared. Having these two derivatives, take the ratio of that of y with x. Note that dt's cancel out, leaving with dy over dx, which is then 3t over 2. With the slopes function figured out, equate this to 0 to locate the critical point. The derivative then becomes 0 as equated to 3/2 of t, making t as 0. With t already known, determine the coordinates of the critical point, and that is through the original equations. From x of 1 plus t squared, plug in t of 0, making 1 plus 0 squared, thus x is 1. Next is from y of t cubed minus 2, or that is 0 cubed minus 2, making y as negative 2. The critical point is then at 1, negative 2. After identifying the critical point's location, take the second derivative in order to know if the point is the highest or the lowest in the curve. What we got is dy over dx equal to 3t over 2. Differentiate it with respect to t, so as to simplify the right term. dt over dt is 1, leaving the coefficient of 3/2 as the second derivative of y with respect to t and x. To take out dt and fix dx, multiply the reciprocal of dx over dt, which is now 1 over 2t. The second derivative of y with respect to x is then 3 over 4t. Next is to substitute t of 0 into the function, making it 3 over 4 times 0, and having a 0 denominator marks the second derivative as indeterminate, which means the second derivative test failed. So we go back to the first derivative test and draw a line to separate tests. This line is for t as equal to 0, so we can assume t of negative 1 on the left. The slope dy over dx of 3t over 2 then becomes rise of negative 1 over 2, or that makes negative 3/2. A negative slope starts at top left and slides down to bottom right. Then assume t of positive 1 on the right. Use this in the slope, which is 3t over 2, making it rise of positive 1 over 2, or 3/2. A positive slope means it starts at bottom left and rises to top right. With concavities figured out, it is then clear that at t of 0, the critical point is a minima.